Welcome students. So now we are going to study about chemical properties of alkynes. Obviously alkynes being unsaturated hydrocarbons are similar to alkenes in their sum of chemical properties. They show addition reactions just like alkenes, but the special case is that terminal alkynes are acidic. Now you will find some chemical reactions especially in alkynes due to acidic character of alkynes. So focus on that because most of the questions of alkynes are based on the acidic character of alkyne. So let's start about it. Chemical properties of alkynes. Actually the terminal alkynes are acidic in nature. Those alkynes which contain a hydrogen triple bond at the terminal carbon show acidic nature, and as they react with strong bases like ammonia to form a conjugated base. So this reaction shows the acidic character of terminal alkynes. Terminal alkynes are acidic in nature. So amine, which is a strong base, can ionize terminal alkynes to form salts, of showing that these are stronger acids. Other strong bases which can oxidize the terminal alkynes are sodium hydrate and LDA. These are the strong bases which can ionize terminal alkynes, showing their acidic properties. Now addition reactions. Alkynes undergo addition reactions. Alkyne contain a triple bond, so they add up two molecules of dihydrogen, halogen, hydrogen halides, etc., showing addition reaction. The formation of the adduct, that means addition reactions of the alkynes, follow Markovnikov rule. Let's focus on addition of hydrogen on alkynes. This takes place according to Markovnikov rule. This is 2-butene. This is a symmetrical alkyne. So in this case there is no problem. Hydrogen will add in the presence of platinum or nickel as a catalyst to form, in first step it will form butene, and followed by further hydrogenation it will form butane. But if it is an asymmetrical alkyne, in that case the addition will follow Markovnikov rule. Now again, the geometry of the product formed, alkene formed by the hydrogenation, depends on the catalyst used. If we use simply hydrogen in the presence of platinum as a catalyst, which we used in the first reaction, cis product is formed, alkene with cis geometry is formed. But if we use lithium in the ammonia, then this reduction of alkynes results in formation of alkenes with trans geometry. Next reaction is addition of halogens. Again, this is a symmetrical alkyne, and in this case halogens like chloride or bromide simply add to form vicinal dihalides, vicinal vinyl dihalides, and further halogenation results in the formation of tetrahaloalkanes. This is a symmetrical alkene. This is alkyne. But in case of non-symmetrical alkynes, just like CH2, C triple bond CH, in this case if we want to add bromine, this will follow CH2 C Br CH Br. Further bromination will result in formation of this type of compound, CH2 C Br, and again a bromine here, the bromine here. Now these are known as tetrahaloalkanes. So tetrahaloalkanes are formed by halogenation of alkynes. Next is addition of hydrogen halides. This follow Markovnikov rule in case of non-symmetrical alkenes. This is a symmetrical one, so hydrogen goes to this carbon and bromine goes to this carbon to form a product bromoethane, which further reacts with HBr to form 1,2-dibromoethane. But in case of non-symmetrical alkyne like CH3, C triple bond CH, this addition will follow Markovnikov rule, according to which the bromine goes to that carbon which contains lesser number of hydrogen atoms, and the product form will be CH3 CBr double bond CH2. Further reaction with HBr will result in formation of CH3 CBr Br CH3. This is 2,2-dibromo propane. So addition was according to Markovnikov rule. Addition of water. One molecule of water adds to alkynes on warming with mercurous sulfates and dilute sulfuric acid at 333 Kelvin to form carbonyl compounds like this. This is propane. When it is warmed with water, H goes to this carbon while OH part goes to the carbon which contains lesser number of hydrogen atoms to form this compound, which undergo isomerization to form propanone. Let's take another example of this. If we reacted with water actually in the presence of mercury and H positive acidic environment, will get CH, OH and yes, CH2 as of the product. Now addition of HCN, addition of hydrogen cyanide. Addition of hydrogen cyanide takes place in the presence of R, C, triple bond, CH. When it is reacted with HCN in the presence of CuCl and it is heated, we get simple addition. HCN part attaches itself to this carbon while hydrogen goes here. We get CN double bond CH2 nitrile. Now another is another important reaction of alkyl halide alkynes is when they are reacted with, let's say this is a compound. If it is reacted with HOCl, reaction with HOCl. This is an important reaction when alkyne is reacted with this compound. Actually this is delta negative and delta positive because oxygen is more electronegative than chlorine. So we get an adduct like this, R. According to Markovnikov rule, negative part goes to that carbon which contains lesser number of hydrogen atoms. It will come here and it will result in formation of this compound, a double bond CH, a chloride here. When it is further reacted with HOCl, again this is negative part, this is positive part. So this again goes to the same carbon and we get a compound like OH, here another OH, and carbon, a chlorine here, another chlorine here, a hydrogen here. Now when this undergo removal of water molecule, a rearrangement, and we get a compound like this OH and this H comes out in the form of water molecule and we get a carbonyl compound CH, Cl, Cl. Next is ozonolysis of alkynes. Alkynes like alkenes also undergo ozonolysis reaction, which is addition of ozone. And in this what happens, let's say we have a compound like let's try to write the general reaction for ozonolysis of alkynes. We have a compound R, C, triple bond, C, R. When it is reacted with ozone, formation of ozonoid takes place in this way. oxygen here, and a double bond remains here, a single bond remains here. Now when this is reacted with hydrogen peroxide zinc, we get this breaks from this place, and on oxidation we get R COOH, and also let's say this was R, this was R dash, so we get R and then R dash COH, we get acids. This was the reaction for ozonolysis of alkynes. Next is polymerization of alkynes. Alkynes also undergo polymerization as alkenes, and there are two types of polymerization actually. The first is linear polymerization, or linear polymerization of ethynes takes place to produce polyacetylene or polyethylene, which is a high molecular weight polymer containing repeating units of CH double bond CH. This is 1,2-butadiene. It can be represented in this form. Next is cyclic polymerization. Actually, let's first write the reaction for this. This is ethine. When n molecules of ethine undergo polymerization, linear polymerization, they result in formation of a compound like this, a polymer like this, addition polymer. This is linear polymerization. In cyclic polymerization, ethine on passing through red hot iron tube at 873 Kelvin undergo cyclic polymerization. Now let's see what is the product formed when cyclic polymerization of ethine takes place. Actually, we can write it in this way: CH triple bond CH. Let's see, here it is CH again triple bond CH, and there is another molecule of ethane, ethine. Now what happens then when it is heated? One bond comes here, from here one bond comes here, this goes at this place, and surprisingly we get a compound with formula like this, alternating single and double bonds. The name of the compound is, yes, we are very familiar with this, it is benzene. Benzene is formed, which can be represented in this way also. So cyclic polymerization of ethene results in formation of benzene. Now this is a solved problem. Here this compound ethine, propyne, is reacted with water in presence of mercury and acid. So it is asking for the compound A which is formed. It is actually C triple bond CH, propyne. When it is reacted with water in presence of acidic mercurous chloride, we get addition product in which this is alcohol, this is alkene, and this undergo rearrangement to form a compound CH3 C double bond O CH3, which is a ketone, acetone. So the correct option is B. Next, which of the following is most acidic? We know from alkane, alkene and alkyne, alkynes are most acidic. So we have methane, we have ethane, CH3, CH3, we have ethine, CH triple bond CH, we have acetylene, CH2, CH2. We know ethine is the most acidic one, alkynes are the most acidic. Next is dichloroacetone can be prepared by reaction. It is asking that how can we prepare dichloroacetone. Let's have a look at this option. In this we are reacting CH3 C triple bond CH with HOCl. This is slightly negative, this is slightly positive. So we get a adduct like this, CH3, COH comes here, double bond, CHCl. On further reaction with the same compound, we get CH3, COH, one OH here, and CHCl2. This undergo removal of water molecule, and the compound which we get is CH3, C double bond O, CHCl2. So it is dichloroacetone. So the correct option is B. So now you must have observed that alkynes are similar to alkenes in their addition reactions, in which they just add with the different compounds because of presence of pi electrons. And apart from this, they show some chemical reactions because of their acidic nature also. In next video, we will discuss about aromatic hydrocarbons. Stay tuned.